Today we're going to complete our discussion of Shor's algorithm. This is a little bit more involved than the other things that we've been doing, so it's not really very feasible to go through all details. So I've prepared a couple of handouts which has them, and you can look at the handouts while I'm going through the lecture, and also afterwards go through it more carefully at your leisure. So you will recall then that we were going to compute, in order to factor integers, this function b to the x mod n, and we were going to try to find the factors p and q of n, and b is chosen to be some integer chosen randomly less than n and no factors in common with n. And this is a function, f of x, and it has a period, and we want to know that period. And if we know that period, which I'm calling r, from that we can factor n using some post-processing. So in this, what we're doing, there's n, the integer n has n0 bits, and that is the number of bits in this register which is computing the values of the function. But the number of values of x has to be bigger than that, because we need to compute many periods of the function in order to compute that period accurately. So it's suggested by Mermim that n, the number which is the number of bits in which the x values are going to be considered, has n bits, where n is twice n0. So we will compute then f of x for all values of x between 0 and 2 to the n minus 1 in parallel. And we were starting to discuss last time how we would do that using modular exponentiation. We have then our input, so this upper layer, these are often called the input qubits because they contain the x values, and the lower ones are often called the output qubits because eventually they contain the function values. And the input will be a linear, there are n of them, and they will contain a linear superposition for all x in that region I said, from 0 to 2 to the n minus 1. We have the output, which will initially be prepared in, the first bit will be 1, and all the others will be 0. So I'm going to describe now how to do the modular exponentiation, and there are n0 of those. And although it says do not cross, I'm going to have to cross, because we also, in order to do this modular exponentiation, we're going to need some work qubits, which will be n0 of those, and they will contain some auxiliary variable as we go along. And the work variable contains an integer b specified by these bits, b0, b1, up to bn0. So the procedure is as follows. Remember, we start with b, and then you will recall we're going to keep squaring. So we put b in this work register. And you multiply the output, which is the function f. This is going to contain the function. By w if x0 is equal to 1. Why are we going to do this? Because we're going to calculate, as we said, b squared, b to the 4th, and so on, b to the 2 to the j for j up to n. And so if x has bits xn minus 1, xn minus 2, x1, x0, then b to the x is product over j, b to the 2 to the j, and we get this, we need this particular factor if xj is equal to 1, so I take it to the power xj. So this is what we're going to compute. This is the function. And we're going to store these values b, then b squared, then b to the 4th in this work register. So we start with w equals b, and we multiply the output by w if x naught equals 1. So that's j equals 0 over there. Wait a minute, let me go. And then we square w. And this is all contained in this auxiliary work register. You multiply the output by the what is the new w, the new work register, if x naught equals, sorry, x1 this time is equal to 1. And you keep doing this n naught times. And for each value of x, this will compute b to the x in a number of operations which is not exponentially large. It's just a power of n, or n naught. So, and the miracle of quantum mechanics says that this is done in parallel for all x. So, this is going to be my description of the Shor algorithm. So what we've already discussed last time is in the input, we feed in an equal superposition of all values of x, and we do that by starting with 0 in the input register and acting with these Hadamard's. So at this point, the state psi naught is an equal superposition of all x values in the input register, the one with n qubits. And for now, the output qubits, which will eventually contain the function, contain 0. So that's here. And then it goes into the modular exponentiation, which computes b to the x mod n efficiently for all x between 0 and 2 to the n minus 1. So and they appear in the output register here, which has n naught qubits. So at this point, we have psi 1. And psi 1 then is an equal superposition over all x from 0 to 2 to the n minus 1. So this is meant to be n there. Of x in the input register and f of x in the output register. So that's here. So what we're going to do next is do a measurement on the output register. So the register contains, you will get some result for the function value. But there's many values of x that give the same function value. Remember, this is a periodic function, and we're going to have many periods in the region that we have x values for. So we get some value F naught. So that's what's indicated here. We measure the output register, and we get, this contains the function values. We get some function value, but then there are many values of x which give that same function value, and they will all be, the wave function will collapse to all the states compatible with this value of the function f naught. So we get, so after we've done the measurement on the output register, we just focus now on the state of the input register, the top line above, and we'll sum, it will contain all the x values compatible with a particular value of the function. So if our function f of x for all the values of x that we've computed contains, let's say, capital Q periods, there will be capital of Q values of x. So let the smallest one be x naught. This is the smallest value of x, which has f of x equal to f naught. But r is the period, so if we add a multiple of r, we will still get the same value of the function f naught. And supposing we have q values of the period. So this is psi 2. So we've measured the output register, and now we're looking at the input register, which is still in a coherent linear superposition of states, because there's many periods, many values of x compatible with this function value f naught. So this is what we have. Now, of course, we haven't a clue what x naught is. So if we just measured this, we just get some value of x naught plus kr. But we don't have a clue what x naught is, so there's no way out of that we could get any information about r. So what we're going to do, and this is the key to Shor's algorithm, is to Fourier transform this function. And when we Fourier, so that's what we're going to describe next. That's what this box here, Fourier transform of 2 to the n variables. So that's what we're going to describe now. And one of the handouts, which you should have in front of you, talks about doing this quantum Fourier transform, which is extremely efficient. So let's consider the effect of the quantum Fourier transform. There'll be n qubits, so I put a subscript n, on a particular state j. So it's the usual definition. It's 1 over the square root of the number of terms, so 2 to the n over 2. This is just the first line up there. Let me write it out again. Sum on k equals 0 to 2 to the n minus 1, e to the 2 pi I. Then this state is j, and the Fourier transform state is labeled by k over 2 to the n times k. So this is our quantum Fourier transform. And we're going to have to figure out how that goes. So the state j we're going to represent it by bits. So the least significant bit is J0. Then it's plus 2 times J1. Each of these J's are 0 or 1, plus 2 squared J2, plus 2 to the n minus 1, Jn minus 1. And similarly for k, is k0 plus 2k1 plus 2 squared k2 plus ... plus 2 to the n minus 1, k of n minus 1. So what we have in the exponential is jk over 2 to the n. So I think I can probably rub this out now and give myself a bit more space. So let's write jk over 2 to the n. Okay, so it's the product of these two terms, j0 plus j plus j1 times 2 plus jn minus 1 times 2 to the n minus 1. I can't clean this well enough. Times the same thing for k, k1 times 2 plus kn minus 1 times 2 to the n minus 1, and all that over 2 to the n. Now we're going to simplify this. And this simplification is essentially also used doing classical Fourier transforms when one does a fast Fourier transform. So it looks like, to do a Fourier transform like this, if we write, say, capital, it looks like there's 2 to the n terms in the sum for each of 2 to the n values of k. So it looks like a classically a naive estimate of the number of operations will be 2 to the n times 2 to the n. But because we'll be able to simplify these, the phase factors, these exponentials, you know already that there's a fast Fourier transform which does it in the number of operations only n times 2 to the n. And the simplifications which we're going to do, which will lead us to the quantum Fourier transform, can also be a way of deriving the fast Fourier transform. However, this particular quantum Fourier transform, which applies to amplitudes of a wave function, will be done in n squared time, so exponentially faster even than the fast Fourier transform, because of the quantum parallelism. So the point is that this is the coefficient up here of e to the I, 2 pi I times that. So any integer part doesn't contribute because e to the 2 pi I times an integer is just 1. So when I expand this out, every time there's an integer, I'm just going to neglect it. So maybe why does this keep going blank? Okay. Capital N is 2 to the little n. So if we just take the terms involving k0 here, we have j0 over 2 to the n plus j1 over 2 to the n minus 1, and so on. Everything comes in, actually, times j of n minus 1 over 2 times k0. But when we go to k1, which is already multiplied by 2, the J0 term is only 2 to the n minus 1. And then J1 is 2 to the n minus 2. And then when we get to Jn minus 2, that's divided by 2. And the term with Jn minus 1 wouldn't be divided by anything. And that would give an integer, which I'm going to drop. So there's one less term in the second line. And then when we go down to the next to the last term, k of n minus 2, so here I'm just writing the same thing out again, quantum Fourier transform. These are the bits of J, and it's going to give rise to a linear combination of terms labeled by these K labels. So this first line is just the same definition as above, but now I write down those exponentials. So for the first bit on the right-hand side, everything is contributing. For the next bit on the right-hand side, we have one fewer term in the exponential. And what's going on here? Right. So the last piece is has only one term in the exponential. So I think this is not easy to follow in detail as we go through it. That's why I gave the handout, so you can go through it afterwards. So now if I write out more explicitly, so for a particular term on the left-hand side, we have a sum of terms on the right-hand side, and over the least significant bit, we have all these exponentials, and over the most significant bit, we only have two terms coming in. So let's consider the simplest case of n equals 2. So we just have 2 bits, so there's 4 terms, 2 squared terms, and for a particular value of the input to the Fourier transform specified by bits J1 and J0, we have a sum. The least significant bit on the right-hand side has 2 terms, 0 plus this exponential times 1, and the more significant bit on the right-hand side has 2 terms, 0 plus e to the 2 pi I J0 over 2 times 1. So I get the coefficient of 0 is 1 over root 2, and the coefficient of 1 is e to the 2 pi I J0 over 2. So it's 1 if J0 is 0, and it's minus 1 e to the pi I if J0 is 1. So if J0 equals 0, then K1 is 1 over root 2, 0 plus 1, and there's a typo here. If J0 is equal to 0, then K1 is 1 over root 2, 0 minus 1. So this transformation, we know, is done by a Hadamard gate. That's exactly what the Hadamard gate does. For the least significant bit, it's a little bit more complicated. I guess I need to decrease the size a bit. For the least significant bit K0, it depends on both bits on the left-hand side, J0 and J1. So the dependence on J1 is still the same e to the pi I, so that's given by a Hadamard gate. But in addition, it depends on the least significant bit on the left-hand side, J0, and this is e to the I pi over 2 equals I if J0 is equal 1. So we're going to need an additional type of gate. We're going to need a controlled phase gate, a gate that will induce a phase of e to the I pi over 2 for the if J0 is equal to 1 on the 1 basis state, but not on the 0 basis state. So we need control phase gates. So if the control qubit is 1, and that was J0 in this case, then the amplitude of the basis state 1 of the target bit acquires a phase. And it was pi over 2 in the case above, and we will need, in general, pi over 2 to the d for integer d equals 1, 2, 3, and so on. So here we have R1. The phase was I pi over 2. So if the control bit is 1, the target qubit is acted on by this operator RD1 on the diagonal for 0, and e to the I pi over 2 to the d on the other diagonal term. If you put d equals 0, you get e to the I pi, which is -1, and this is just the control Z gate that we discussed earlier in the course. So these control phase gates are generalizations of the controlled Z gate that we mentioned earlier. So a schematic diagram of how this quantum Fourier transform works for the simple case of 2 qubits. So J1, that's the more significant qubit. Well, let's do J0, the less significant qubit. That goes through a Hadamard, which means that if J0 is 0, K1 is a linear superposition of 0 and 1, and if J0 is equal to 1, K1 is a linear superposition of 0 minus 1. When we go to J1, first of all, it acts with this Hadamard. That tells us how this state, the least significant bit on the right-hand side will depend on the most significant bit on the left-hand side. But also, we have this control R1 gate here. So if J0 is equal to 1, we get an extra phase of pi over 2 into K0. So we're going to have Hadamards and control phase gates. All right. So looking at that for a while, you can convince yourself that if we go to, whoops, what was, yeah. That if we go to 3 qubits, you find that for J0, it's the same as before, it's just a Hadamard. For J1, it's the same as before, it's H, and it's a phase, control phase gate R1. But for J2, we have a Hadamard, but then we have a control phase gate with a phase of pi over 4, R2, depending on J0, and a control phase gate of pi over 2, depending on J1. So you have to sort of sit down and think about those formulae in the handout and convince yourself that this is true. So I think it needs some more thought than what we have time to do in the lecture, but that's what the handout is for. So if we try to extrapolate to arbitrary n, then, so we have n qubits. So for a particular set of computational basis states on the left-hand side, J0 up to Jn minus 1, the output on the right-hand side, each of these will be a linear combination of computational basis states as determined by this circuit diagram. And you see that for J0, we just have one Hadamard. For J1, as before, one Hadamard and one control phase gate. For J2, we have one Hadamard and 2 control phase gates. And for J of n minus 1, we have a Hadamard and n minus 1 control phase gates. So this R of n minus 1 just requires a very small phase. So there are n Hadamards here, and something like n minus 1 over 2 control phase gates. So, and you see that this has to be done in sequential order. So the number of control phase gates is n minus 1 over 2. So in other words, it's of order n squared gates, which have to be done sequentially. So this quantum Fourier transform will act in a number of operations of order n squared. The number of Hadamards is only of order n, so that's a lower count. Okay. So this is the super fast quantum Fourier transform. It's a Fourier transform of the basis states. And if we have 2 to the n terms, it acts in a time of order n squared, which compares with which is exponentially faster than a fast Fourier transform, classically, which is n times 2 to the n, which in turn is exponentially faster than a naive Fourier transform, which is 2 to the n times 2 to the n. So, of course, this is, as usual, a bit of an illusion, because we can't extract all those 2 to the n Fourier coefficients out of our computer. We have to do a measurement, and then we just get one of them. Okay. So now we are going to discuss what we do when we've got this Fourier transform. Just as a light respite, in Nielsen and Chung's book, they also have a light respite at some point, and you need it reading that book, and you probably need it listening to this lecture. They quote a limerick by Peter Shaw and his wife about quantum computing. And I've actually lightly edited this limerick, so I think it flows a bit better. When computers we build become quantum, then spies of all faction will want them. Our codes will all fail, and they'll hack our email, but crypto that's quantum will daunt them. And in addition to this being a light interlude, there is something in that last line, but crypto that's quantum will daunt them. So we've seen then that if you could build a quantum computer, you could break the standard classical codes using a quantum computer. But also, the quantum computer raises other possibilities of encrypting in a quantum way, which would not be decodable by these methods. So that's what the last line of the limerick is referring to. So we will go to here. Okay. So before we do the Fourier transform, we have this state which I wrote down somewhere over here. And the number of terms in the sum is the number of periods, so the total number of values of x is 2 to the n, and the period is r, and so the number of periods, the number of terms in this sum is 2 to the n over r, and in general, and it's true in the example which is gone through in this handout, r is not a power of 2, and so 2 to the n over r is not an integer, so we have to take the integer part. So what happens when we do the Fourier transform of this? We will skip some of this stuff. So this is just writing down the Fourier transform in the usual way, and I think I wrote it down somewhere over here. That's this. And that's what we get after we've done the Fourier transform routine. It's a large number of terms, and the output will be a linear combination of states psi of y for all possible values of y. But the point is, if we have a periodic function, and we have many periods, and we Fourier transform, the Fourier transform has sharp spikes at multiples of essentially 1 over the period. There was a question. Yes. Thank you. It should be a while. And there is, yes, thank you. So this is a standard sort of sum, which you do when calculating X-ray scattering and stuff like that. It's basically a geometric series, so I'm not going to go through the details of doing that calculation, but, well, wait, no. So that's the value, that's the state, and then the probability of getting a particular output y is the square of the magnitude of that, which is this. And the nice thing is that when I take the square of the absolute value, the dependence on x0 cancels out. It's just a phase, and it's a constant phase independent of y, and it cancels out. And so this is the expression for the probability of getting a particular value of y. So we have to do this sum. Where's it over here? So if you look at this exponentially to the 2 pi I k r y over 2 to the n, then all these terms will add up in phase. In other words, we'll get a big peak when, if y is equal to a multiple m of 2 to the n over r. So if y is a multiple of 2 to the n over r, the 2 to the n's cancel, the r cancels, and we get 2 pi I k times this multiple n, and that's 1. So everything adds up in phase if y were equal to this value. Now, as we said, in general, r is not a power of 2, so actually this is not an integer. But what we measure is an integer. So what we hope is that we will be able to, this will be sufficiently strongly peaked that when I measure what comes out of the Fourier transform, and I get a single value of y, that y will be close to one of these values. It will be, we hope it will be very close to a multiple of 2 to the n over r. Because if it is, I have a fighting chance of being able to figure out what r is, the period from that. Okay. So I've taken then a particular example. Which was the one I discussed before with where we're trying to factor n equals 91. So of course that's 13 times 7. This contains 7 qubits because 2 to the 7 is 128. This is the power of 2, the smallest power of 2 greater than 91. So I need n naught equals 7 bits to store 91. And according to Mermim, to make sure you have a large number of periods in the result, you need to take the number of x values as 2n naught, which was 14. Sorry, the number of bits. So the number of x values goes from up to, there are 2 to the n x values, which is 16,384. So as we discussed last time, the period in this case, and we're going to choose the random integer less than n with no factors in common with n, is going to be b equals 4. And we know, because we did it, that the period is r equals 6. So how many periods do I have in the result? Well, it's 16,384 divided by 6, which is a huge number of periods. According to Mermim, I need at least n, at least 91 periods. Well, with many more than that. So we're doing a bit of an overkill, but that's better maybe than an underkill. So I worked out numerically then, for this example, what P of y is. And you see there are indeed sharp spikes. Remember, this is the Fourier transform. And there are 6 spikes, including one at 0. One at 0 is not actually very useful, but there is a dot there. 1, 2, 3, 4, 5, 6, because the period is 6. And you see you get very, very sharp peaks. Now, we said that everything would add up in phase at some value which is not an integer, but presumably these sharp peaks are the nearest integer to those real values. And there's a high, so you can, I think, see there's a pretty high probability that I'm going to land, when I measure y, on one of these sharp peaks. And if I land on one of these sharp peaks, then I know that I am within, that this is the nearest integer to a multiple of 2 to the n over r. Peaks at integer y close to 2 to the n over r. Let's just hear about the normalization. There are 6 spikes, and the weight on each of those 6 spikes is supposed to be the same when you do the calculations, 1/6, and you can see that that seems to be correct. So the probability that I get something adds up to 1, but all these probabilities are completely dominated by these spikes, which is exactly what I want. So let's supposing we look at the second peak and blow that up. So these are the integer values of y that you could get out. This dashed line is 2. This is the second peak. So the peaks are multiples of 2 to the n over r. So this is the second peak. So this is 2 times 2 to the n over r, which happens to be 5,461.33. And you see the actual probabilities of the integers don't quite land on the peak because this number is not an integer. But you see this one is very big and the others are relatively small. So the total weight in all these red histograms is 16.167, and you see most of that is in the biggest one. So if we are lucky and we land on this or the corresponding peak for the histogram for the other peaks, then I know that this is the integer closest to a multiple of 2 to the n over r. And what I want is r, and it's not quite obvious how we get r out of that, but yes. Yeah. There we are. Okay. It turns out because this is the third spike and 3 is exactly 1/2 of 6, that this number is an integer. So it fits bang on the maximum. Whereas for the other peaks, the absolute maximum would occur at a non-integer value, and this is the nearest integer. So if you do the sum, let's assume then we had that expression for P of y, and we sum it up. And let's assume that we take an integer value y close to where the peak would be for real y, ym. In general, that's not an integer, plus delta. And it's a standard calculation, which you've surely seen before in the context of X-ray diffraction and so on, that in the vicinity of one of those peaks, the probability of y is, first of all, there's a factor 1 over r, and that's just because there are r peaks, which all will have equal weight. And then it's sine of pi delta over pi delta squared. Now, so I'm going to show you again the next figure, which is a blow-up of this second peak, right? Greatly expanded scale. And that function, sine pi delta over pi delta squared, considering things to be a function of a continuous variable, that's what this continuous blue curve is, which peaks at this fractional value here. And this peak is the nearest integer to it. Now, if I'd done this for the third peak, you ask why are the peaks of different height. If I'd done this for the third peak, this height, its peak here, would be an integer. And there would be a red bar there, which actually would contain all the weight, because all the other integers are at the zeros. Okay. Right, so you see this, this works out reasonably well. Where's the rest of my handout? Okay. So using this quantum Fourier transform and making sure we have a very large number of periods of the function with some reasonably high probability, we end up on one of these bigger spikes, and we're the nearest integer to a multiple of 2 to the n over r. So how do we try to find the period out? Remember, that's what we wanted to do. Okay, so. And again, I think if you want more details on these mathematical aspects, it's best to look at Mermim in various appendices in Mermim's book. You see, Shor's algorithm has many parts to it, and the quantum is only part of it. At the end, there's quite a bit of processing that has to be done, which we will talk a little bit about now. So what we have computed is a multiple so what we measure y. So y is close to an integer multiple of 2 to the n over the period. So let's divide by 2 to the n. That's a big number. This should be close to a multiple of 1 over r. Right, we Fourier transform, so the spacing is 1 over r. And this is done by continued fractions. So if we call this x, we compute a continued fraction representation of x. So to explain what you do, if there's an integer part to x, let's call that c0. And let's write the remainder as 1 over x1. So x1 is less than 1, so 1 over x1 is greater than 1. So let the integer part of x1 be c1. And call the inverse of the remainder x2. And we could keep doing this, so if we do that, then one more stage, x is c0 plus 1 over, and x1 is c1 plus 1 over x2. And you can keep doing this. So we get the continued fraction representation, c0 plus 1 over c1 plus 1 over c2 plus and so on. And these c's, these ci's, are called the denominators in the problem. Now, if you do a continued fraction representation of a rational number, that is to say a ratio of two integers, then the continued fraction will eventually terminate. But if you have an irrational number, then the continued fraction will go on forever. Here, of course, we have a rational number. It's a ratio of two integers. So there's a theorem which is quoted by Mermim, that the best guess for x, which is this multiple of y over, it's a multiple of 1 over r. Oh, I should mention that if you stop the partial fraction at some point, these are called partial sums. So you can work out a succession of partial sums. And the best guess for x is the partial sum having the largest denominator less than n. Which is 91 in this case. So for the particular example in our numerics, we hit the peak in the largest histogram, which was at 5461. And 2 to the n is 16384. So this is, of course, is a rational number, so this continued fraction will terminate. And you do the calculation. C0 is 0, obviously it's less than 1. C1 is 3. And C2 is 5461, which is certainly bigger than n. So all we have is, so an integer multiple m of 1 over r is equal to 1 over c1, 1 over 3. So r is 3m. We don't know what m is, but we can just try some small values and see what works. Because you can try m equals 1, that gives you r equals 3. If you calculate b cubed mod n, you do not get 1. But if you put m equals 2, then you confirm that it's the period. Find m equals 2, but because that corresponded to the second peak, but of course, when you did the measurement, you didn't know that. You just get one number out. You don't know which of the peaks it corresponds to. So you find m equals 2 by trial and okay, so I think I managed not to erase this. This is then the summary of Shor's algorithm, all the different stages, and the final output, the final result is an integer y, which if you did everything correctly and were a little bit lucky, has a high probability of being the nearest integer to a multiple of 2 to the n over r, in which case, using this continued fraction method, you can estimate r. And this is what we want. When we have r, as I showed before, and that's also written out in this handout which you got, you can use that to factor n into its 2 prime factors. Okay. All right, well, that went a bit quickly, but anyway, if you have answer questions, and you can, if you want, you can go over that handout afterwards. So the last topic in these lectures is actually a very important one, and that is quantum error correction. So I guess yeah. So as we'll discuss, quantum error correction is essential. But for a long time, it was thought, for reasons which we'll discuss shortly, to be impossible in principle. So when it was realized that you could do quantum error correction, and this was realized, I think, independently in 1995 by Peter Shor again, and also Steen. This was a huge advance in quantum computing, that quantum error correction could, at least in principle, be done, because without it, a useful quantum computing was clearly going to be impossible. With it, it's a tremendous technical challenge, but not completely impossible in principle. So let's talk first about classical error correction. And then because some of the ideas we will take over to the quantum case. Now I should first say that in computing on a normal computer, error correction is not necessary. The hardware for a classical bit is huge on an atomic scale. And also, the states of the classical bit, 0 and 1, are very, very different. So the probability of an unwanted flip is incredibly tiny. However, classical error correction is necessary for transmitting information down a noisy channel. The signal attenuates, there's some noise, and some bits might get corrupted. So what is a standard way of dealing with that? If some of the bits get flipped, how can we tell? So a simple way is that each logical bit is represented by 3 actual physical bits. So a classical bit 0 is represented by 3 bits, each 0. And let me write that more compactly, because I'm using this quantum notation, which isn't necessary for the classical case, but it means the transition to the quantum will be straightforward. So we replace the bit by 3 bits, and if that bit is 0, if the logical bit is 0, then all 3 bits are 0, and if the logical bit is 1, the 3 physical bit are all 1. So we have to monitor these 3 bits from time to time and look for flips. In particular, we look to see if all 3 bits, let's call this a code word, all 3 bits in the code word are the same or not. If they're all the same, we presume that is the correct answer. But supposing they're not all the same, supposing when we get to the end of our noisy channel, we get 2 is 0 and 1 is 1. Yes, so we want to send a 0, but we send it 3 times. 0, 0, 0. And we check at the end these groups of 3. If there are no flips, each group of 3 should all be the same, either all 0s or all 1s. But supposing I get something like this. The natural thing to do, which is what one does, is use a majority rule. We assume, we're supposing that the probability of a flip is small, so much less likely that 2 bits flipped than 1 bit flipped. So we would observe it, we would see this, and we would error correct to 0, 0, 0. So we're doing, this is the simplest thing you could do, which is to take 3, because then there's a majority rule. Well, this is for a single bit. Each individual bit is sent in triple. So if you wanted to send, say, 2 bits, 0, 1, this would be expanded to 0, 0, 0, and this would be expanded to 1, 1, 1. And when you get to the other end of your line, you would look at the first 3, and when you look at the second 3, and are all these 3 the same? If they are, we assume that's correct. If they're not all the same, we use the majority rule, and the same for this. So quantum error correction also uses multi-qubit code words and monitoring, but there are several major differences. First of all, quantum computing requires error correction. In many cases, the physical systems representing the qubits are extremely small and can very easily be disturbed, often on an atomic scale. Any small quantum outside interference can disrupt the quantum state. So, in contrast to the classical case, checking for the errors is problematic. How would I check for an error? Well, what do? I observe the state. But if you observe a quantum mechanical state, in general, you change it. If you're observing, as we are, in the computational basis, and this bit is actually in a linear combination of 0 and 1, if you observe it, you will change that state. It will either be 0 with some probability or 1 with some probability. So this is obviously no good, and it's for this reason that for some time it was thought that quantum error correction was impossible, because to do error correction you have to measure, but measure changes the state. Another difference with classical error correction is bit flips are not the only errors. We can also have phase changes. So instead of 0 going to 1, which is a bit flip, you can also have phase errors. So in particular, if the relative phase of the state 0 plus 1, if that was kicked to 0 minus 1, that has no analog classically, but there's a phase change of pi now. The phase between the 0 and 1 components is flipped by pi, so you can have phase errors as well as bit flip errors. And finally, unlike the classical case where it's all or nothing, it's either 0 or it's 1, and you know you're not going to get anything else, errors for qubits can arise gradually and continuously out of an uncorrupted state. So that in particular seems to indicate it will be very difficult to correct for errors if they can gradually grow with time. Well, let's start to see what we can do. How can we overcome these problems? So we're going to start off with a simple case where we're going to just assume the only errors are bit flip errors, same as the classically. Once we've done that, it will be not as difficult as you think to figure out how to correct for phase errors. Okay. So we're going to take a simple case where we assume only bit flip errors. So if these are rare, one might hope to correct them by tripling the number of qubits, just as we did in the classical case, and then do some sort of majority rule or something like this. So if we're considering a single logical bit, which in general can be in a linear combination of the 0 and 1 computational basis states. So what we would like to do then is to represent this physically by a linear combination of 3 qubits all with 0 plus 3 qubits all with 1. And actually that turns out not to be too difficult from what we've already done, just using control NOT gates. So we're going to draw the circuit here. So this is psi. And we're going to, of course, we're going to need 2 other qubits because we're going to need 3 altogether, and we'll initialize those to be 0. And we will have C-NOT gates, 2 C-NOT gates, which are controlled by the original bit with psi. And the target qubits are these two extras, which we're going to have to bring into play to triplicate the number of bits. I like to write the C0 gate in the notation where I indicate an X, because the X operator that's what it does. It flips the bits. So this is more explicit as to what is going on. So what comes out here? So we have to consider the 0 and the 1 separately, and then use linearity to get the sum of what comes out. So if we consider the 0 here, what does this, if this bit is 0, does this one get flipped? No, because the C0 gate only flips when the control bit is 1. So if we consider the first one being 0, since we initialize the second one to be 0 and it's not flipped, it becomes 0, and similarly for the third one. And then if we now add the piece of the initial wave function, which is 1, so it's beta times 1, then the C0 gate flips this one, so 0 becomes 1, and it flips the third bit, 0 becomes 1. And this is what I want. Okay, so we've used linearity. We first of all considered what comes out with 0 inputted here and what comes out with 1 inputted here, and then we formed the linear combination alpha for 0 and beta for 1. Okay. So we have to guard then against any of these 3 qubits being flipped. So remember, we're only assuming bit flips errors. So possibly this one might get flipped. So I indicate with an X, but a dashed line around it to indicate maybe. And similarly for this. And similarly for this. Okay. So we're going to assume that at most 1 bit is flipped. So essentially assuming that the error rate is small, and we neglect the probability that 2 bits are corrupted. So the uncorrupted state is then alpha 0, 0 plus beta 1, 1, 1. But there can be 3 possible corrupted bits, corrupted states, corresponding to each of the 3 bits getting a flip. So it will be alpha 0, 0, 1 plus beta 1, 1, 0. That's where the right-hand bit is corrupted, or the middle bit is corrupted, or the left-hand bit is corrupted. So if the state is uncorrupted, we're going to leave it alone. But if the state is corrupted to one of these states, we have to first of all detect it and then correct it. And of course, we can't just measure it like that, because we destroy this linear superposition. So, destroys the coherent superposition. So it looks like at this point that it's impossible to do quantum error correction. But then it was realized that one could try the following. We introduce additional ancillary qubits. We're going to couple the ancillary qubits to our 3 qubits of interest here, and we're going to measure just the ancillary qubits. And that will give us enough information about whether there's been bit flips without destroying the coherent superposition of our state here. Okay. All right. So we have 2 ancillary qubits, which I will initialize with 0, I think, yes. So these are the ancillas. And we're going to have them with control NOT gates, where the ancillas are the target, and the 3 qubits that we want to know about are the control qubit. So for example, let's take the first of the 3 that we're interested in, and let's do a control NOT to the first one. Let's take the second of our 3 of interest and do the same. And then we take the second of our 3 of interest and connect that to the lower ancilla, and the third one connected to the lower ancilla. And then we measure the ancilla. And this maybe will give 0 or 1, x is 0 or 1, y is 0 or 1. So notice that we have not destroyed the coherent superposition in these 3 bits, which are the qubits of interest. Okay. So supposing, I think I'm going to stop and I'll let you think about it before the next lecture to complete the picture. But supposing nothing has been corrupted. All right, so this is a linear combination of 0, 0, 0. Let's put this in then. So this, okay, so it's a linear combination of 0, 0, 0 plus 1, 1, 1. So let's consider, so again, we have to do linear superposition. Let's consider the bit with 0, 0, 0. Now, these are the controls. So if the control qubit is 0, nothing is changed. So this doesn't flip, this doesn't flip, this doesn't flip, this doesn't flip. So since I started with 0 and there's no flips, so uncorrupted, at least for the 0, 0 part, I would get x equals 0, y equals 0. But then it looks as if I then do the 1, 1, 1 piece, I'm going to get flips. But I'm always going to get an even number of flips, the way this is cooked up. So if it's 1, 1, 1, this bit flips here, but then it flips back here. This bit flips here, and it flips back here. So for both 0, 0, 0 and 1, 1, 1, I get x equals y equals 0. So I'm going to leave it as an exercise for the student, which we will go over in the lecture tomorrow. What happens for those other 3 corrupted states? We will see we get different and unique values for X and Y. Okay, so I'll stop here.
So the uncorrupted states that we're considering, we've considered only 3 types. There can be more, right?
You're talking about the corrupted states?
Sorry, corrupted state, yeah.
Yes, that's right. Well, there can be phase flips too, which we will discuss in the next lecture. I'm just considering the possibility of bit flips at the moment, just to...
No, even then, I think for the alpha case, like where there's a bit flip for like 0, 0, 1, and then beta also changes. I mean, do we really have to have this?
Well, that would really be 2 flips, wouldn't it? I mean, you have this linear superposition, and if you act to flip the bit, I guess it will flip both pieces, no?
Okay, yeah.
Otherwise, I think we're talking about 2-bit flips, which is less likely. Okay. It can happen, but it's a lower probability.
So it's just the first order that we're...
Yes, first order, right. Okay.